Today I wanted to go through a couple of examples of how to draw Lewis dot structures. Now we have our rules in the upper right, and we have a periodic table for use of reference. So the first example we're going to do is actually a ionic species where we have magnesium oxide. And so I want to get a little practice for drawing Lewis dot structures for individual atoms and then molecules. So to begin with, we have magnesium, and we need to find that on the periodic table. So this has 12 protons, so it's here on the third row, second column. So to figure out how many valence electrons it has, we simply just have to count from the left. We go 1, 2, and so we know it has 2 valence electrons. So I'm going to add those in on our magnesium. Now whenever you're adding in your dots to represent electrons, you normally want to start on one particular side. I normally say start with the top, then you can go to a different side. So we're going to go top, right, bottom, left in general. There's no common convention for what that has to be, but you do want to do one electron on each side to begin with. Alright, so now we have our 2 dots on magnesium. Now we need to draw in our valence electrons for oxygen. Now oxygen is over here with 8 protons, and so again we're going to start on the left side of that row and count 1, 2, 3, 4, 5, 6. So oxygen has 6 valence electrons. So I'm going to start adding these in. So I'm going to add 1 to each of the 4 sides. 1, 2, 3, 4. And once you get all 4 sides filled up, now you're going to start pairing up your electrons. 5, 6. Alright, so now we have all 6 of our valence electrons drawn. Now what's going to happen here is we have a metal and a non-metal coming together. So we're going to have an ionic bond that occurs. And this means that the magnesium is going to give up its electrons, and the oxygen is going to take those in. And so if I redraw our Lewis dot structure, it's not going to be very exciting. Magnesium essentially has nothing on it. I mean, technically it has 8 valence electrons, but it's over here on the neon section. But generally you'd want to draw it without electrons in this case to show that it lost its electrons. And I'm going to go ahead and draw these other 2 electrons that came from the magnesium in red, just to help highlight where they came from. But now you can see that we have 8 valence electrons around oxygen and no electrons around the magnesium. In truth, it's really 8. And then we need to also add in our charges because this is an ionic species. And so for that, you would write a 2 plus on the magnesium and a 2 minus on oxygen, showing that magnesium lost 2 electrons and oxygen gained 2 electrons. So this is an example for how you can draw Lewis dot structures for individual atoms and how you can kind of do it in a reaction for an ionic species. Now I want to go ahead and do another example. Give me just a second. Alright, so typically what we'll come across are not ionic species that we want to draw Lewis dot structures for. Typically we want to do it for ones that are having covalent bonds. So this is normally when you have 2 nonmetals coming together. Such is the case for carbon tetrachloride, or CCl4. Generally this is used as a dry cleaning solvent or as a refrigerant for fuel. It's also one of the most toxic things for your liver. So for carbon tetrachloride, we're going to go through and follow our rules over here that we went through on the last video. So first thing we want to do is we want to place the atom with the lowest number in the center of our species. Then, and to do that, we need to figure out which one is the most electronegative. So we have two elements here. We have carbon and we have chlorine. So we have carbon over here, and then we have chlorine over here. Now we need to decide which one of these is closest to fluorine. Chlorine is just one below fluorine, and carbon is 3 to the left of fluorine. So I would say that chlorine is the most electronegative, and since we want the least electronegative, we're going to choose carbon to be our central atom. So I'm going to draw carbon in the middle, and I'm going to surround that with chlorines. Now generally for low dot structures, you want to draw everything in the coordinate system, so top, right, bottom, left, something of that nature. But sometimes you'll see low dot structures drawn with a little bit more of actual structure drawn. It's not truly a low dot structure, but it's similar to it. Alright, so the next order of business is we need to determine our number of valence electrons. So to do that, we're going to do it for each species. So I'm going to go ahead and start off with the chlorines. So for chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. Sorry, I should have started on the third row here. Same principle though. So it has seven valence electrons. So we're going to say 7 electrons, and we're going to represent electrons with a E minus, multiplied by the number of chlorine atoms that we have. In this case, we have 4 chlorine atoms. So we're going to multiply that by 4, and 7 times 4 gives us 28 electrons coming from the chlorines. Now we need to do it for same thing for the carbon. For carbon, we need to count its valence electrons. We go 1, 2, 3, 4. So it has 4 valence electrons. So we have 4 electrons here. We're going to multiply this by our number of carbons in our molecule. We only have 1. And so 4 times 1 is 4 electrons. So now we want to add all these up. So 28 plus 4 gives us 32 electrons. Alright. Now following our list of rules here, we want to draw in all the single bonds. So we're assuming this makes an actual molecule, so I need to draw in some sort of bonding between each of my atoms. So I'm going to draw in a single bond between the carbon and all the chlorines. Then we go on to our next step where we need to distribute the remaining electrons and start off with the most electronegative species first. So in this case, this will be chlorine. Now, all the chlorines are the same. We can start with any one that we choose. I'm going to go ahead and start off with the one on the right. And so basically what we want to do is we want to make sure it has 8 electrons surrounding it. So we have this bond here, and this represents 2 electrons. So we need 6 more electrons to be around our chlorine. So I'm going to go 1, 2, 3. Now I can start pairing them up. 4, 5, 6. So we used up 6 electrons. Our chlorine is now obeying the octet rule, and so we're going to move on to the next species. And I'm going to just choose this bottom chlorine here. Alright, so I'm going to continue count from where I had my electrons previously. So 7, 8, 9, 10, 11, 12. Now that one's complete. 13, 14, 15, 16, 17, 18 electrons so far. Then 19, 20, 21, 22, 23, 24. 24 electrons. So now we want to make sure that everything worked out. So originally we had 32 electrons. We used some in the bonds. So we had 4 bonds multiplied by 2 electrons each, and that'll give us 8 electrons in total for our bonds. And then the individual dots, as I just counted out for you guys, we essentially had 24 dots. So 24 times 1 electron will give us 24 electrons. So if we do 8 plus 24 electrons, that will give us 32 electrons. And so we want to make sure that both these answers match. If they don't, then there's something else we need to do. Now the other thing we want to check is to make sure that our central atom, carbon, obeys the octet rule as well. So it has 1, 2, 3, 4 bonds. Multiply that by 2 electrons each. That gives us 8 electrons, so it's obeying the octet rule as well. So every atom is obeying the octet rule. We used up all of our valence electrons, so this molecule is done. So we're going to do another example. Give me just a second. All right. And then for our next example, we are going to take a look at thionyl chloride. So thionyl chloride is SoCl2. It's commonly used in lithium batteries. It's the positive electrode or cathode. And for this one, we have three species to look at. We have the sulfur, oxygen, and chlorine. All right. So let's take a look and figure out which one is. We're trying to find our least electronegative species. So we look at fluorine. If we go down 1, that's our chlorine. If we go to the left 1, that's our oxygen. And then if we go down and left 1, that's sulfur. So our sulfur is going to be our least electronegative species because it is below oxygen and it's to the left of chlorine as well. So it must be our least electronegative species. All right. So we're going to go ahead and put our sulfur in the middle, and then we're going to surround it with our other atoms. So we're going to put oxygen, chlorine, chlorine, and it doesn't have to be exactly in this order as far as up, down, left, right, but you want something of this nature. Then we want to figure out our total number of valence electrons. So I'm going to start off with oxygen. And then for our oxygen, we can just count over from the left side of its row. So 1, 2, 3, 4, 5, 6. 6 valence electrons. So we have 6 valence electrons. We only have 1 oxygen. So that's going to be equal to 6 electrons in total for oxygen. Then we have chlorine. And for chlorine, we go 1, 2, 3, 4, 5, 6, 7 valence electrons. And in this case, we have 2 chlorines. So we're going to multiply that by 2, giving us 14 electrons, or 14 valence electrons for our chlorine species. And last, we're going to do sulfur. Alright, and it's the exact same thing we did for oxygen. We're going to just count over 1, 2, 3, 4, 5, 6 valence electrons. So we have 6 valence electrons for sulfur. We only have 1 sulfur atom. And so that's going to be 6 valence electrons for all the sulfur species. Add all those up. We do 6 plus 14 plus 6. That should give us 26 valence electrons. And then we need to start drawing in our single bonds. So I'm going to draw in a single bond between sulfur and all of our other species, so the oxygen and the 2 chlorines. And then we need to fill in our remaining electrons. So another method for figuring out how many electrons you have to work with is you can take our 26 to begin with, subtract out the number of bonds. So we have 1, 2, 3 bonds. So we're going to have 3 times 2 electrons, 2 for each bond, and that's going to give us 6 electrons used up in bonding. So we can subtract that out, and we know we have 20 electrons remaining. This is actually my preference for how you draw Lewis dot structures, as you won't use up more electrons than you have, but there's a lot of different ways to do this. So oxygen is actually our most electronegative species. Again, oxygen and chlorine, that'd be hard to determine between the two, but oxygen does win out. But you could still do this one without knowing that information. Alright, so for the oxygen, I'm going to draw on 1, 2, 3 electrons. Then I'll start pairing them up. 4, 5, 6. Now I can move on to the chlorines now that oxygen has 8 electrons around it, 2 in the bond and 6 dots. And I'm going to choose the right chlorine just because. 7, 8, 9, 10, 11, 12. And now I can move on to the next chlorine. 13, 14, 15, 16, 17, 18. Alright, so now both of our chlorines obey the octet rule. Our oxygen is obeying the octet rule. We used up 18 of our 20 electrons, and I need to put these other 2 electrons somewhere. Now, looking at our sulfur, we can see that we have 1, 2, 3 bonds on it, meaning there's only 6 electrons. So it's still missing 2 electrons to get to its full octet, or to have 8 electrons. So now we're going to go 19, 20. We used up all of our 20 electrons, and now we can do a happiness check on sulfur and see that we have 6 electrons in bonds, and then 2 electrons in dots, giving us a total of 8, so it's obeying the octet rule as well. So everything looks good. I'd recommend doing one final check. I'm going to go ahead and do this in red, just so it makes things look a little bit nicer. So again, we have 3 bonds with 2 electrons each, giving us 6 electrons. And then we have 6 from this chlorine, 6 from this chlorine, 6 from this chlorine, giving us 12. 6 from this oxygen, bring us up to 18, and then 2 from sulfur, bring us up to 20. So we can say we have 20 dots times 1 electron each, giving us 20 electrons. Add that up, we get 26 electrons. And we can confirm that that matches with our original amount of valence electrons that we started out with. So this is the Lewis dot structure for thionyl chloride, or SOCl2. And I know it seems a little silly, but I highly recommend that you guys double check your valence electrons, as that can help save you, especially on exams and quizzes. Alright, so we'll move on to another example. This one's a little bit different, as you'll come to find out in just a moment. So this one is carbon dioxide, or CO2, and CO2 is normally used for dry cleaning. It's highly used in dry cleaning industry, and you know, it's also what we breathe out and what keeps plants alive. So pretty cool little molecule. So for this one, we need to determine if carbon or oxygen is the least electronegative atom. So we start off looking at fluorine. We see that oxygen is just 1 to the left of it, and then we can see that carbon is 3 to the left. So carbon is going to be our least electronegative atom, so that's the one we need to put in the middle. So I'm going to put carbon right up here, and then I'm going to surround this with oxygens. And again, there's a number of ways you can do this. I'm going to put it in on the left-right just because I know what the structure is going to end up being, and it would be shameful not to do that correctly. Then what we want to do is we want to count up our number of valence electrons. So I'm going to start off with our oxygens. Alright, we already determined last time that oxygen has 6 valence electrons. And again, you can just do that by counting on the periodic table, starting from the left of that row. We're going to multiply that by 2, because we have 2 oxygens in this molecule. And that'll give us 12 valence electrons for oxygen. Then we need to do it for carbon. Carbon, as we determined previously, has 4 valence electrons. Again, you can just count up on the periodic table, starting from the left, just counting the elements. We have 1 carbon, so that's going to provide, not 6, that's going to provide 4 valence electrons. Add all those up together, and we get 16 valence electrons for this molecule. Now I want to draw in our single bonds. So I'm going to draw in a bond between the carbon and each of the oxygens. We have 2 bonds at 2 electrons each. So that's going to be 4 electrons used in bonding. If we subtract that from our original 16 valence electrons, that's going to give us 12 electrons to work with to try to make everything obey the octet rule. So I'm going to start off with our oxygens. So we're going to go 1, 2, 3, and I start pairing them up, 4, 5, 6. This oxygen has 8 electrons around it, 2 in the bond, 6 in the dots. Now I can go on to the next one. 7, 8, 9, 10, 11, 12. Alright, so we've used up all of our electrons, and this oxygen is obeying the octet rule. It has 2 in the bonds and 6 dots for a total of 8. So you might think that we're done now, but our problem is this carbon. This carbon only has 2 bonds on it for a total of 4 electrons, so it's not obeying the octet rule. So whenever you find yourself in a situation where you are out of electrons to use, and you're not obeying the octet rule for all your atoms, this is when we're going to introduce multiple bonds. Now the way to do that is you're going to choose a pair of electrons. I'm going to choose this top pair of electrons on this oxygen, and that's going to get moved over into forming a bond between the carbon and oxygen. So I'm going to redraw my molecule now with a double bond between the carbon and oxygen on the right. Draw in my dots, and then we can check to see if we're obeying the octet rule now. Now I didn't add any electrons, so we're still at our maximum of 16 valence electrons. So counting all this up, our oxygen has 2 bonds, so 4 electrons in bonds, 4 dots, 4 electrons in dots for 8 total electrons, so it's obeying the octet rule. This one hasn't changed, still 6 dots and 1 bond for 8 electrons. And our carbon now has 3 bonds at 2 electrons each, so it's at 6 electrons. So it's not quite at 8. So now I need to borrow 2 more electrons. Now, if we took from this oxygen, that wouldn't be that favorable. Oxygen is very electronegative. It does not want to share the majority of its electrons with the carbon. But this other oxygen here is a little electron rich. So this is the one we actually want to pull from. So in this case, we're going to steal 2 electrons from the oxygen and put that into a bond between the carbon and oxygen. And so now if we redraw this again, we'll have our oxygen, a double bond with our carbon, double bond with the oxygen, draw in our lone electrons again. Alright, trying to get them in. Alright, and so now I'm going to draw a little red line here so that that doesn't get mixed up with the other dots we had. Alright, so now if we look at this, we have 2 bonds on this oxygen and 4 dots for a total of 8 electrons. This one has 2 bonds and 4 dots for a total of 8 electrons. And the carbon has 4 bonds for a total of 8 electrons, so it's obeying the octet rule. So right now, all of our species are obeying the octet rule. We're going to go ahead and double check to make sure we have the correct number of electrons. So we have, in total now, we have 1, 2, 3, 4 bonds. So we're going to have 4 bonds at 2 electrons each, giving us a total of 8 electrons. And then we have 4 dots on this oxygen, 4 dots on the other oxygen for a total of 8 dots at 1 electron each, giving us a total of 8 electrons. We add that together and we get 16 electrons. So now we have 16 electrons that are being used, and we start off with 16 valence electrons, so all that works out. Alright, so I want to do another example that would involve multiple bonds. And this time we're going to have acetylene be our example. So acetylene is kind of cool. It's used in welding. Y'all may have heard of acetylene torches. And this is the species that is half of the fuel for that. So acetylene is C2H2. So we need to look at carbon and hydrogen. And I've told you in the past that carbon and hydrogen are actually very similar electronegativity-wise. Carbon is a little bit more electronegative than hydrogen. But the other thing is hydrogen, it only needs 1 electron to get up to a noble gas configuration, so it can only make 1 bond. So since it can't really make multiple bonds, we're going to have to put the carbons in the middle. So I'm going to do 2 carbons and then 2 hydrogens on the edge here. There's other configurations you could try, but ultimately you end up with a carbon with 4 bonds, and that wouldn't work out too well. So this is probably the better drawing of a Lewis-Dot structure for it. You would eventually get here, but it might take a little trial and error. So we're going to have HCCH. Now we're going to draw in our single bonds. Okay. And I forgot to add in our valence electrons, so let's go ahead and add those up really fast. So I'm going to start off with carbon. Carbon has 4 valence electrons. And we have 2 carbons. So that gives us a total of 8 valence electrons for all of our carbons. For hydrogen, that only has 1 valence electron. And so we're going to multiply that by 2 since we have 2 hydrogens, giving us a total of 2 electrons for our hydrogens. We're going to add those up together, and we'll have 10 valence electrons to work with. Now if we go ahead and subtract out the bonds that we already drew in, we have 1, 2, 3 bonds. 3 bonds times 2 electrons each for a total of 6 electrons. We have our original 10 electrons that we counted up for our valence. Subtract those out, and we get 4 remaining electrons that we have to work with. Now, I'm going to just choose one electron or one carbon. I'm going to go ahead and choose the carbon on the right, and I'm going to add in 1, 2, 3, 4. Alright, so I've added in our 4 electrons, and we can see that we have 2 bonds on it, and we have 4 dots on it, so it's obeying the octet rule. Our hydrogen has 1 bond on it for 2 electrons, and for hydrogen, that means it's happy. It only needs 2 electrons. It is at that helium noble gas configuration. Same for the one over here. It has 1 bond, so 2 electrons, so it's good. The main issue is this carbon. This carbon only has 2 bonds, so it only has 4 electrons around it, 4 valence electrons around it. So it doesn't obey the octet rule. So in order to take care of that, we're going to take a pair of electrons from our neighboring species and put it into the bond. And when we do that, we'll have H, C, double bond, C, H. And we'll still have our 2 electrons on our carbon here. And when we go to look at this, our carbon down here is still good. We have 3 bonds for 6 electrons plus the 2 dots, bringing it up to 8 electrons. So it's good. Our hydrogens are still good. They each have 2 electrons still within the bonds. And then this carbon has 3 bonds for a total of 6 electrons. So it's not quite there yet. So we're going to have to take 2 more electrons from a neighboring species, in this case this carbon, and put it between the bond. And so this is going to form a triple bond. And so we're going to have H, C, triple bond, C, single bond, H. Alright, and so this is our actual Lewis dot structure for acetylene. The hydrogen has 2 electrons from the bond. This hydrogen has 2 electrons from the bond. This carbon has 4 bonds, so 2 electrons each, giving it 8 valence electrons. Same with this one, and so they're both obeying the octet rule, and so everything is good. We also want to double check to make sure all of our electrons add up. So we have 5 bonds at 2 electrons each for a total of 10 electrons. We have 0 dots at 1 electron each, giving us 0 electrons. And so we have a total of 10 electrons, or 10 valence electrons with what we have drawn. And so that checks out. That matches with what we previously counted for our valence electrons. And so this is how you draw a structure for acetylene. So you can have double bonds, you can use triple bonds if you need to. You can never use 4 bonds between a species. That has yet to be proven to exist. Alright, so there's one last topic I did want to discuss with you guys while we're going through examples. And that is resonance structures. And so to help demonstrate resonance structures, I was going to go through ozone as an example. Now, ozone is kind of important. It's what helps protect us from radiation from the sun. And as you can imagine, all the oxygens are the same. So we're going to put an oxygen in the middle. I'm going to go ahead and draw this as a bent structure because it is in real life. And so we have our oxygens. We need to draw in a single bond between all of them. And if you go through and figure this out, you'll decide, oh, we need to draw in a double bond in order to have everything obey the octet rule. And so if you went through all the Lewis dot structure protocol we have been doing, you'd see that we'd have 4 dots on the oxygen on the left, with a double bond to the oxygen in the middle with 2 dots on it. And then we end up with 6 dots on the oxygen on the right with a single bond connected to central oxygen. And we can go through and double check to make sure this does work out. So we're going to go ahead and say oxygen has 6 valence electrons. We have 3 oxygens in total. So this is 18 valence electrons. For our bonds, we have 3 bonds at 2 electrons each. And then we have 4 on the first oxygen, 2 on the middle oxygen, and 6 on the last oxygen, for a total of 12 dots at 1 electron each. I'm sorry, I forgot to give the total for the bonds. 3 times 2 is 6, and 12 times 1 is 12. Add those up, we get 18 electrons, and so this checks out with those 2. Now, one of the things that you would come across is you'd have to decide which of these oxygens on the outside you want to steal an electron from. And so in order to take care of that, in truth, it could be either one of them. And so there's an equal chance that it would come from, say, the oxygen on the right as opposed to the oxygen on the left. And so we essentially get a mirror image of what we had just drawn. And this would be a viable Lewis dot structure as well. Now, in truth, both of these species exist. And they actually alternate between the 2 of them. So they're actually going back and forth between them on having this one have something like a pi bond or 2 or a double bond, and this one having a pi bond or a double bond. Now, in actuality, what this equates to is this will end up with a overall structure that has something a little bit in the middle of both of these. So we'll have our oxygen structure. We're going to draw in our single bonds between them. And a lot of times it can be represented with a kind of dashed line. Let's try and make that look a little bit more dashed here. A dashed line going between this bond and this bond. And to show us a little bit more delocalized, a lot of times I'll go ahead and show the overall arc between the 3 species. And then to round out your dots, you'd actually draw your pair of electrons on the central one, and then only 2 pairs on each of the others. And so what this line and dash is truly representing is something like a 1.5 bond, as opposed to a 1 or single bond or a 2 or double bond. And so the actual structure is actually a mixture of these 2, and since they have equal abilities of existing, is essentially a 50% composition of this and a 50% composition of that, giving an overall structure of this, where this oxygen is a distance of some distance between a double and single bond between those 2, as well as this one. As opposed to when we actually look at this, we don't see this one having a shorter distance half the time as opposed to this one. Normally double bonds equal shorter distances. And so this is how you do a resonance structure. I'm going to show you one more example of a resonance structure. And in this case we're going to do pyridine, which is kind of cool because it is a ring structure. Alright, so for pyridine, this is C5H5N. And I'll be honest, for this one, it might be a little difficult for you to know that it would be a ring. But I did want to introduce you to this just so you are aware that it does exist. Alright, so we have our general backbone here. We'd have hydrogens by each of the carbons. And then I draw in my single bonds. And nitrogen's fairly electronegative compared to carbon. And we'd also end up having to have double bonds between essentially alternating carbons in there. And so this obeys the Ottec structure. You can check it out for yourself if you like. But if we were to draw the exact same species, and I'll try to draw it in the same order here. Where we have our carbons and nitrogens all arranged the same. I'm going to draw our hydrogens in here as well. Our nitrogen is still going to have a lone pair of electrons. But this time we could actually have the other carbon species having double bonds. Alright. And so in this case, both of these have a 50-50 chance of being essentially the correct structure. They both exist, and they exist for half the time. And so we actually need a combination of these two. Now, I'm going to go ahead and draw the combination over here, just so it's a little bit easier to see. So if we actually combine those two resonance structures, we'll have our carbon backbone and nitrogen on the bottom. We'll have all of our hydrogens. I'm a little bit out of space here, but that's okay. And we'd have a lone pair of electrons on the nitrogen. Ideally, that'd be drawn on the bottom. I'm just out of space. And then to show that, say, this bond is 50% of the time a double bond and 50% of the time a single bond, we would draw in it being dotted. Now, this is true for all of the bonds in here. So one way of drawing this is to draw in a dashed line all the way around. Now, whenever we have a ring structure, sometimes, because chemists try to be efficient, and drawing dashed lines is sometimes a little difficult, instead of drawing a dashed line, they'll just draw a circle in the middle. So if you ever have a ring structure and you have this resonance structure going on where you have something like a 1.5 bond order, then you will normally draw in a circle, or if you want to use dashed lines, that's fine too. But this is how you would draw the resonance structure for pyridine. Alright, so hopefully these examples helped you out. In general, for the Lewis dot structures, what I'm expecting for this course is that you'd be able to draw it for the molecules that we did beforehand, and I wanted you to at least recognize what resonance structures are, but we probably won't have too many of those. Alright, so thank you, and I hope to catch you in the next video.